CBAF, the Continuous Electron Beam Accelerator Facility, is a new laboratory for basic nuclear physics research. At CBAF, scientists can advance their understanding of matter itself by probing the quarks and gluons in the atom's nucleus with beams of electrons from a superconducting accelerator. CBAF has an educational mission as well. The CBAF Science Series features scientists and engineers who are gifted at making their work not only informative, but fun. The Science Series is held once a month during the school year in the CBAF Center Auditorium. The presentation is live, spontaneous, and for the most part, unrehearsed.
Good evening and welcome. Before we get started, we want to make sure you all notice that there is a date change for next month, Exploring the Submarine Volcanoes, A New Frontier. It's going to be Wednesday, May 25th. The speaker today is Charles Hyde-Wright. He's here from ODU. He was born and raised in Berkeley, California. He attended Berkeley Public Schools. In high school, his main interests were math, music. He played the clarinet, soccer, and French. He always wanted to be a scientist. He was strongly influenced by his father, who was a nuclear chemist and worked on basic research at Lawrence Berkeley Laboratories in Berkeley, California for 35 years. He was drawn to science by the idea of understanding how things work and how everything is connected together, and the amazing toys or instruments that science produces. Charles Hyde-Wright did not actually take physics until he was in college at the University of California in San Diego, where he received a BA. He quickly decided he loved it, and he found that it was the most fundamental and mathematical of all of the scientists. He did his graduate work at MIT. While at MIT, he did his research at MIT Bates Linear Accelerator, where he worked on his PhD thesis. He received the Peter Domez Award from the Accelerator Users Group for his PhD dissertation. From 1987 to 1993, he was an associate professor of physics at the University of Washington in Seattle, Washington. He was a recipient of the Presidential Young Investigators Award from the National Science Foundation. I am pleased and proud to present Charles Hyde-Wright. Thank you.
Well, thank you. Good evening. Welcome for coming. So I want to have a little fun here with you tonight. Let me put up a few things here. So as mentioned, I've been teaching physics as well as doing research for some years now. And one of the things that I've been thinking about as I teach introductory physics is that I like to have some demonstrations that illustrate the fundamental principles that I'm trying to teach, but specifically demonstrations that can be done by the audience, that if I give a lecture, whether it's to a university audience or to a more general audience, that excuse me, people can go home, reproduce the demonstrations, and think about the physics on their own, and not just in the pressure of a quick-paced lecture. So what I want to do tonight is present to you three such demonstrations that you could, in fact, in some form or another, repeat easily at home. One of them is a little more spectacular tonight, but I'll give you a version of it that you can do at home as well. And I have three basic principles that I want to illustrate with these. The first is that air is heavy, and the second is that air pressure is enormous, and the third is that information is energy. And there are some other principles that will come along as we go through this. In particular, the universality of physics is very important to what I have to say tonight. The idea that a concept that we develop in one domain then will have important consequences in radically different domains. And another concept that will come out of this is that the dimension of space matters. The fact that we move around in a three-dimensional space has profound impact to the world, but we can also do physics and have phenomena that's based on 2 dimensions, 1 dimension, or even 0 dimensions, as we'll see. So talk a little bit about the universality of physics, first of all. In one of the ancient schools of philosophy from the Greeks, there were 4 elements: earth, air, fire, and water. And with these four elements, there were two forces, gravity and levity. And it was sort of a matter of common sense that gravity acted on earth and water, holding rocks down to the earth and water down to the earth. And levity acted on air and fire. It pushed the air up, and fire arises. Well, we have a little different view of the world today. We believe we have evidence that there's a small zoo of subatomic particles, and that the forces are universal. In particular, gravity acts on everything. And then plus there are also nuclear and electromagnetic forces. It's not any tidier a view than the ancient Greek view, but we think we have a lot more evidence for it than we believe they had. Just as an aside, one of the purposes of the canceled superconducting supercollider in Texas was to test our ideas that the nuclear and electromagnetic forces can be unified into one framework. And one of the purposes of this laboratory of CBAF is to help us try to figure out how ordinary matter is created out of the nuclear force. We think we understand the basic principles of the nuclear force, but we really don't understand very well how you actually build stuff out of the equations that we have for the nuclear force. Okay, so for my first demonstration, I want to contrast this ancient Greek idea of levity pushing air up versus our more modern view that gravity pulls everything down. So we have some understanding of gravity from things like baseballs and rocks, and now we want to see that gravity acts on air the same as it acts on everything else. So in particular, what I want to do is I want to show that a balloon full of air is heavier than an empty balloon. So for this purpose, I made a little balance here, deliberately crude, just so that I can play with it. So first thing I want to do is get my balloon balanced with enough paper clips and whatnot. Here we go. Whoops. Okay, now that's a little too much. And then after I have this balanced, I'm going to blow up the balloon and try to convince you that the balloon is heavier when it's full of air than when it's empty. Okay, that's actually pretty well balanced. Let's see what happens. It doesn't matter. I mean, I haven't determined that the lengths of each side are exactly the same. I don't really care about that. I just care that I can put enough paper clips on there so that this is well balanced. Put a little extra here. A piece of tape might help. Just bring it down just a little bit. Kind of whatever works. Okay, so if it's perfectly balanced, it'll hang horizontally. If it's unbalanced, it'll hang a little bit up or down. As it goes up or down a little bit, friction in this crude bearing becomes enough to hold it in place, so it doesn't actually, even if it's unbalanced a little bit, it doesn't flip all the way horizontal or vertical. Okay, so now that was pretty well balanced, so let me try blowing up the balloon. Now, I'm putting a lot more air in the balloon than would be in the same volume. If I have this volume of the balloon here, if I imagine sort of drawing a volume of air here that's the same size, I've got more air inside because I'm getting higher pressure to push out the stretchy balloon. A little more for good measure. The idea is that I do this until I hyperventilate. Okay. Now I don't want to tie this because I want to be able to let the air out when I'm done in a fairly controlled way. Okay. Now actually, if we could cut off the air circulation for a moment, it might help a little bit so that it doesn't bounce around with the... Okay, okay. So the balloon hangs down considerably below where it was before when I didn't have any air in it. So now I want to do two things. First of all, I want to see how many paper clips I have to add to make it balance again. Let's see. Well, so I'll start out by adding 2. And that's about right. Maybe, let's see. I want to stabilize it. Now, I don't know, maybe a third one. I think a third one's going to be too much. Well, that's pretty good. Okay. So the extra weight of the extra air in the balloon is about equal to the weight of adding 3 paper clips on that side. Okay, now just in case you're skeptical and you think that maybe I added something extra to the balloon when I blew it up like a little bit of water, let me try to let the air out in a reasonably controlled way. Okay. Now, let's see. Let me put up. Okay, so that thing bounces around as the air comes out. Maybe we'll just let it rip a little while. So if indeed, as the air goes out, I'll just tell you a little bit more about it. If indeed gravity is pulling down on the air, then, for example, every square inch of the floor or every square inch of the ground outside has pushing down on it the weight of the entire column of air all the way up to the top of the atmosphere. But if indeed gravity pulls air down the same way it pulls me down to the floor, or it pulls something down as I drop it, then we have a little bit of a puzzle as to why all the air isn't down around our ankles. I mean, after all, the air is up. The ancient Greeks said that air has a force of levity acting on it, not a force of gravity, because it was obvious that the air was up. But in fact, we see that. So I claim that I've at least suggested that gravity is pulling down on air now that we have let all the air out of the balloon. The balloon went up by a certain amount. And if I take off the paper clips again, it should balance. Oh, took off too many. There we go. Okay, so took off the 3 paper clips again, and it's approximately, well, a little overdone. Okay, so every square inch on the ground bears the weight of the entire column of the atmosphere. And that produces our atmospheric pressure of 14.7 pounds per square inch, which is also equal to the weight of a column of mercury 30 inches tall. So when they talk about the pressure is, the barometer is 30 and falling, it's the pressure that day is the same as the weight of 30 inches of a column of 30 inches of mercury. but it's dropping because the pressure fluctuates a little bit. Okay, so if gravity is pulling down on air, why isn't the air all down around our ankles? Well, because the air that's already down around our ankles is pushing back on the air above it by that same pressure of 14.7 pounds for every square inch. So this was just a warm-up. What I really want to do now is show that this is an enormous pressure and that there are enormous forces associated with atmospheric pressure that come directly as a consequence of this idea, which is actually rather counterintuitive, that gravity acts on everything, including air. So to illustrate that, first step to illustrate that this is that this pressure is very large, let me consider if I step on the scale. Now, actually, things have gotten better since I wrote the transparency. It only says 160 pounds tonight. But if I step on the scale, gravity's pulling down on me, and then the bottoms of my shoes are pushing down on the scale, and the scale says I'm pushing down by 160 pounds. And the area of my feet, they're about 11 inches long by about 3 inches wide, using the square foot approximation here, or a rectangular foot approximation. So the surface area of my feet is about 66 square inches. So if I take 170 pounds and divide it by 66 square inches, I get a pressure of 2.6 pounds per square inch. So if I were to, if instead of standing on the scale, if one of you came down and lay down here and I were to stand on you, that would be very uncomfortable. And yet that's only a very small pressure compared to this atmospheric pressure. Okay, but yet we don't seem to feel that any tremendous pressure just walking around here. I don't feel like I'm being squeezed on all sides. So that seems a little puzzling. So how can we demonstrate that, in fact, there is this enormous atmospheric pressure? So let me consider this drum over here. It's a 50-gallon drum. Its surface area is roughly 3,000 square inches. Take the top and the bottom and the side all the way around it. It's about 3,000 square inches. There's 14.7 pounds per square inch. There's over 40,000 pounds of force of the atmosphere pushing on this. If our modern view of physics is right and the ancient Greeks are wrong. 40,000 pounds, that's 20 tons. It's an enormous force. How come the drum doesn't collapse? Any suggestions? Yeah? Better than approximately equal. Because the lid's off. The air pressure inside is the same. So in fact, there's 20 tons of force pushing out from the inside that completely balances the 20 tons pushing in from the outside. And that's the same reason why we don't collapse, because there's air dissolved inside our tissues and our blood, and that pushes out on us in the same, exactly balancing the air on the outside pushing in. So that explains why the drum doesn't collapse, but it also tells us how we can make this enormous force manifest, how we can make the drum collapse. And that is by simply removing the air that's inside of it, or removing some significant fraction. I mean, 20 tons, even a ton will easily collapse that drum. So we just have to remove some fraction of this. Okay, so here's a procedure for how to remove the air. I'm going to first of all put some water in here. Okay, now we have to, I'll be right back. I'll explain our procedures in just a minute. I actually said finger tight. So we're going to, for safety reasons, we want to keep the gas can out here. Yeah, you want this one. That one goes in there to hold, and then this one. Oops. And that's fine. Okay. Let me check the gas. Okay. Okay, turn the gas on. Okay, here we go. Okay. So we're going to heat the water in there so that it's boiling, so that the steam will push some fraction of the air out of the can, and that also the air inside the can will get hot to the boiling temperature of water. And then when we're done, well, I want to let it run for about 5 minutes. It turns out the more we heat up the can, the better it works, as I'll explain in a minute. Before I get to that part, I want to talk a little bit about the safety issues here, because this is somewhat of a hazardous exercise, and I want to make sure that you appreciate that. There are, first of all, some obvious hazards that we've got a burner going in here, so there's a fire hazard. Pardon? So so we deal with that first of all by having the gas can outside, and we have some fire extinguishers handy. The next hazard is that we're going to make this can hot. The top is still fairly cool. You can see it's starting to steam a little bit. So the can is hot to the touch. You could get a burn from touching it. Those are both fairly obvious hazards and therefore fairly easy to deal with. But there's a third hazard which will become evident as we go on, which is that we're going to make this thing collapse very spontaneously and without warning, very catastrophically. And you don't want to be touching it when it collapses, because there could be a severe pinching hazard. Okay, so it's steaming fairly nicely, and I want to let it sit for a few minutes because we need the can to be good and hot in order for this to work well. So I wanted to take a few minutes while we're waiting for this to tell you a little more about myself, since I don't have any good jokes to tell you tonight. It's true that I studied a lot of mathematics in high school and earlier. Also, for me, it was particularly interesting. I learned a lot of mathematics outside of school. I learned a lot from my father, who taught me many things very early when I was in elementary school. But to me, it's also very significant that my mother also taught me a lot of mathematics. And I can remember specific things that my father taught me about negative numbers, for example. And I can remember my mother teaching me about set theory. And I can remember my sister teaching me about exponents when she had just learned them and I was several years younger, and I was just learning multiplication. And she said, hey, you know, look, you can do this other thing with multiplication as well. So I got mathematics from many, many very personal sources. I also mentioned that I studied French quite a lot in high school, studied from about 7th grade through high school. And I liked that a lot. It was a very interesting kind of intellectual challenge to keep all this straight and all these rules and master all this vocabulary. But I got kind of tired with it. It was a lot of work to learn a foreign language. But I had the opportunity in college to spend a year at the University of Grenoble in France. And that was really a wonderful change, because then I had a chance to really use the French, to get used to listening to it all day long, to speak it, and to just become comfortable with it and not to think about it anymore and just do it, just speak it. Now, it used to be that foreign languages were essential to science. Physics, you had to learn either French or German, probably mostly German, because that was the language of the literature. After World War II, that became less and less important because more and more both of the written and spoken language of science is English. But that really masks something more important, which is that there are scientists all over the world, and they all have to learn English in order to be scientists. But it's as much the difficulty for them to learn English as it is for us to learn their languages. And they appreciate it enormously when Americans and others learn their language. And in fact, by studying French, it created many opportunities for me. It gave me great pleasure, both personally and professionally. After I got my doctoral degree, I had the opportunity to get a NATO fellowship to go to a laboratory near Paris for 6 months and work with the French group there. And I have continued to collaborate with them in a number of ways. And it has been very, very interesting. Recently, as we prepare to do experiments here in this laboratory, every time we have an idea, we have to very carefully think it out ahead of time, develop the idea, write a document that defends what we want to do, why we want to do it, how we're going to do it. I went through this procedure last fall with a group from France. They came over and visited for a few days, went back to France, came back a couple weeks later. For them, it was kind of difficult to come here and make a very quick transition to speaking English intensively for several days and then going home for a couple weeks and then come back again. So we just did the whole process in French. And so there were a few days while I was working in this laboratory where I probably spoke more French than I did English. So it's been really very exciting for me to have put in that effort, and it has had many rewards that I never anticipated when I was studying French. Okay. So let's see. I think this should be. Yeah, that's okay. So that's pretty hot. It steams off of there. Give it another minute. Let's see. Okay, I got my. After I crank it off, you can go. You can turn it off out there. After you do that. Okay, so I think that should be hot enough. Turn the fire off. Now I want to seal this up quickly. This is sort of overkill, but what the heck. Okay, you want to take it away? Okay, so now what are we doing? So we turned off the gas, sealed it up. It always does that right away, and then it sits there and does nothing for a long time. Okay, so we had 1 atmosphere of hot air and water vapor inside there. 1 atmosphere of pressure, that 14.7 pounds per square inch, on the inside pushing out. But now the pressure inside is dropping because the air inside is cooling off, and more importantly, as the water inside cools off, it condenses back to water, leaving behind nothing. So we're going to have this 20 tons of force on the outside pushing in and less on the inside pushing out. So the idea is that something exciting is going to happen. And I can't tell you when. Okay, well, you can see it's still very hot. Here. Okay. Woo! There we go. Boy, that's a record, I think. That only took about 2 minutes. Okay. So don't mess with air pressure. There's actually, see, every time I do these things, I learn something new. This illustrates another phenomenon. I didn't make any transparencies about this. I didn't think about. Okay, tell you what I want to do with this. It might. I think it's fairly stable as far as it's not going to collapse anymore. But I want to relieve the air pressure because it's actually. You hear that hiss? There's still a big imbalance of pressure. Once I let the pressure out, then I pretty much only have to worry, or let the air back in, I pretty much only have to worry about the hazard of it being hot. I don't have to worry about it collapsing on me any further. Okay, well, that's not going to go. Let's see. Steve, where are those gloves? I don't want to talk about this without it. There we go. Here. There. I think that's pretty stable. Thank you. Okay, so this actually, just looking at this, it made me think of something else that I think I should talk to you about. This illustrates another principle that is very important to modern physics called spontaneous symmetry breaking. We started out with a symmetrical can, circular. There are no, other than the lids on the top, there's no preferred orientation. A circle is a circle no matter how you turn it. When the can collapses, it collapses into approximately an equilateral triangle. You know, you've got triangular sides here. There's a point in the back and 2 points here in front. Sometimes when I've done this, it's a little more symmetric than this one. This one really went bang. So it indented here. But it's approximately a triangle. But which way? So it's a triangle like this, but it could have been a triangle oriented in any way. It had complete freedom of how to make that triangle with any orientation. The apex could have been here, could have been here, could have been here, could have been here, could have been here. In order for it to collapse, it had to choose. It had to break that symmetry. It had to say, no, I'm going to put the apex here and the flat surface here. I'm not going to put the apex here and the flat surface here. And in some sense, it's waiting, trying to figure out how to break the symmetry. Which way it's going to go is why it takes so long. Because the drum is very strong as long as it's circular. As soon as something starts to give, then boom, it's very weak and it collapses. So this is a phenomenon of symmetry breaking because it's no longer symmetrical all the way around. It has a preferred orientation now. Okay, now I was expecting that this was going to take a while because sometimes it does. So I wanted to, so while I was waiting, I was going to show you how to do this at home on a slightly less spectacular scale, but still effective. So if you put a little water in a jug, something that you can put in the microwave, or you can capture steam off of a kettle, but so heat the water up there until it's boiling. So we're going to fill that jug with steam, and then we'll cap it. And as I've done this, I've discovered that almost anything works as a cap. First time I did it, I worked very hard to get instead of a milk jug, I got an orange juice jug that had a screw cap. Another time I took a piece of plastic wrap and a rubber band and put the plastic wrap over it and put the rubber band about 5 times so it was really tight. it worked so well that I decided just to go back to the milk jug, and that seems to be working. So we'll see how that does tonight. So if you heat the water to boiling, take it out. Be careful that you don't burn yourself. And then cap it somehow. And then just wait. And if you get impatient, you can put it in the refrigerator or in the freezer to cool it down a little faster. This is all, okay. It's almost done. Yeah.
Over here.
Yeah.
Is there any theory, does one apex get chosen and the others follow suit, or do they all happen simultaneously, or does anybody know?
It probably, okay, the question was, I emphasized that it has to choose which face to collapse or where to have the apex at any point around the perimeter. And the question was, once it makes that choice, do they all go simultaneously or does it sort of propagate around? I don't know. I would say that it propagates around. I'll come back to that. Let me just see if this is, well, might be, let me put it in for another minute. Should be almost melting the thing. The point is it's gonna start to collapse at some point. Either that it starts to bow in here or it starts to develop a little crease, and then it's going to start to go in. And then at that point, this becomes a new strong point, so then that makes this side weaker again. I mean, once it starts to collapse on this side, that also weakens it on this side. If you took really fast photography, you would probably see some interesting waves as the ripple, as it starts to propagate around. And my guess is that it would start from some center, some weak spot, and then propagate around. But I really don't know better than that. Yeah, another question in the back.
Yeah, instead of just leaving the can and throwing it out like that, couldn't you just put the top back on it, put the water back in, reboil it to fill it back out?
Yeah, I consider that dangerous. First of all, now that the can is creased, you're not going to get your perfect can back. And if you tried, and in order to, and it's quite strong in this configuration, so you're going to have to get a lot of overpressure in order to force it back out. And that's what I'm nervous about, because you might blow the lid off. Okay, this is hot enough. So if you just cap that and let it sit there, it should eventually scrunch itself more slowly than this one. So if you were to turn the burner back on now that it's sealed up and try to push this back out again, I think you'd have to get a very large pressure in the inside before you would do much, push this out by very much. At that point, you might start. Actually this one I think is welded, but if it were just crimped, you might start breaking that, undoing that crimp. So that's actually much less controlled than what we did here. So I would rather not try it. Any other questions or comments? Okay, so I said one of the themes was the sort of universality of physics. So we started out by making some comments about gravity, as it's sort of familiar to us from sort of ordinary objects being pulled down to Earth by gravity. And then I tried to persuade you that gravity also acts on fluids, air, and as well as water. And that as a consequence of that, we have this very dramatic phenomenon of air pressure. There's a whole other field that comes out of this, which is the science of fluids and of hot and cold, or thermodynamics, the dynamics of hot and cold. So the rest of my talk deals with this subject in a way that I find a lot of fun. I have this thing that I call the entropy engine, or the chocolate chip motor. And like a lot of engines, it has to be primed. So I'm going to start it up, and then I'll talk about it. And by the time I'm done talking about it, it ought to be about working. Okay, so this is where the title of my talk tonight comes from. So I'm going to put some soda pop in this beaker. And I'm going to add some chocolate chips. Now, I first saw this in my son's preschool class when he was about 3 years old. And somebody was doing this as a demonstration. They gave a lecture on Piaget's ideas of child development and then gave this as an example of something that might amuse little children. And being a little child myself, I mean, as she was starting to do this, I hadn't a clue what it was about. And then she dropped the chocolate chips in, and something started to happen. And this whole story that I'm about to tell you just sort of flashed through my eyes, or through my mind. So I find this thing quite exciting. Okay. So it takes a little priming, so we'll leave it there, see what it does. Here, let's clear this away. They have to get a little waterlogged in order for it to work well. Okay, that's about right. Okay, so what is this all about? Well, I have this word entropy. Entropy is the word that we use in science for the measure of disorder. Now, disorder is something that we're all very familiar with, although it's perhaps maybe surprising or puzzling that it's something that we could measure. That we could give a number and say the amount of disorder is 5 in some units of disorder. But by disorder, I really mean exactly what the word means. I mean, I like to illustrate this with my office, which most of the time is a terrible mess. And in fact, the principle of messiness is so important to physics that it's given a name called the second law of thermodynamics, which says, for example, there are many ways of writing expressing this, but one way is to say that an ordered system will naturally tend to disorder. So suppose I start out in some fantastic morning and I come into my office and everything is perfectly organized. All the papers are neatly filed away or stacked up in labeled piles. All the books are on the shelves. And then I just go to work and do the things that I need to do every day. Pull out some books and papers and prepare a lecture. Then I go off to lecture, leaving some of the books scattered on the table. I come back from lecture, and now I have the mail has arrived, so I bring the mail in, and I start sorting it. But there's some things that I'm not sure what I want to do with them, whether I want to throw them away or read them or file them away, so they pile up. A colleague comes in with a question and a computer printout, and we throw a computer printout on the table and leaf through it. Then pretty soon it's lunchtime, and so we leave. And you repeat this process a few times, and pretty soon the office is a complete mess again, with papers scattered everywhere in piles that don't quite make any sense. That's sort of the natural state. Conversely, equivalently, it's quite obvious that it requires energy to create order out of disorder. I mean, once my office reaches this condition where there are papers piled on the floors and on the desk and on every available surface, it takes me at least an entire day of solid effort to put that back into order, to figure out which papers to throw away, which ones to file with which other ones, return a few books to their rightful owners if they don't belong to me. This takes a lot of energy to create order out of the disorder that always seems to naturally develop. So the first two statements are actually, I think, fairly obvious. But they lead to a rather startling conclusion. Namely, that order is a form of stored energy. That it's not in the thing. I mean, if I organize all of my papers properly so that I can find any particular paper when somebody comes in and asks about it, there's energy there not in the paper itself, but in the fact that the papers are organized. And that's what I want to try to convince you of with this thing I call the entropy engine. Yeah, that's working beautifully right now. So the point of this is that the second law of thermodynamics also works in reverse. The natural tendency of any ordered system, any system that's nicely organized, will naturally tend to become disordered. And that natural tendency can be exploited to do work, to produce useful energy. Useful energy meaning the kind of energy you use to drive a car up a mountain or pump water out of a well. Thermodynamics was basically developed out of the necessity of using coal to pump water out of wells and do other processes for the Industrial Revolution in Britain and elsewhere in Europe. So very succinctly, as order goes to disorder, we can extract energy. So how is that happening with this system here? So I have, so my apparatus is a clean beaker, some soda pop, some chocolate chips. And in this process, I take an ordered system, initially highly organized system, and convert it into entropy, namely disorder, and energy. So where is the order, where is the organization, where is the disorganization, where is the energy in this system? Well, first of all, the soda pop is in a very ordered state. I've got lots of information about the soda pop because I know that there's a huge amount of carbon dioxide in this very small volume of the soda pop. And I also know that that order will spontaneously disappear because eventually if I leave the soda pop out, the carbon dioxide will go into the atmosphere and I will no longer have any knowledge about where it is other than it's somewhere in the atmosphere surrounding the Earth. So I've lost information about the CO2 molecules. And all I have left is sugar water. Somehow it doesn't taste the same without the soda pop. So I have information that I have lots of CO2 in a small volume, and eventually I lose that information because now all I know is that the CO2 is in a very large volume. So I have a very specially engineered catalyst that speeds up this natural process. I mean, this natural process might take about 20 minutes normally, but I've cleverly engineered a very special catalyst which will speed up this process of liberating the CO2 out of the soda pop and into the atmosphere. And this very specially engineered catalyst is the chocolate chip. Okay, so in what sense are how are the chocolate chips speeding this process up? Well, let me make a digression now. Talk about another principle of physics that comes into this, which has to do with the dimensionality of space. So the first step in why the chocolate chips speed up the transition from order to disorder is the fact that the chocolate chips speed up the formation of bubbles. You notice that all those chips are coated with little bubbles of CO2. And the reason why they attract the bubbles has to do with the question of the dimensionality of space. So We can speak of different spatial dimensions. We move around in a world of 3 dimensions. Right, left, front, back, up, and down. So that's a volume, 3-dimensional volume. But we can also think about 2 dimensions, the surface. I mean, we actually, in some sense, spend our time more in a 2-dimensional world because we're always walking around on the surface of the Earth. It's only with great difficulty that we can really fully exploit the 3rd dimension. Or we can have an idea of a 1-dimensional space in which we're constrained to move on a single line. We can go back and forth, but we can only move on a line. Or 0 dimensions, if there's something that has us nailed to the spot, and we can't move around from one spot. So in order to make a bubble of CO2, we have to have lots of molecules get together and push the sugar water out of the way. And in 3 dimensions, this is very hard to do. If you think about playing tag in 3 dimensions, if you're playing tag where you're chasing each other and you have to actually touch the other person's hand, then if you get close, you can move in the 3rd dimension and easily avoid. So it's very hard for the molecules to get together in 3 dimensions because there's so many escape routes. In 2 dimensions, it's a little easier, but it's still hard for the molecules to get together. So if the molecules are stuck on the surface of the chocolate chip, it's easier for them to get together than if they're just roaming around in the water, but it's still pretty hard for them to get together. If the molecules are stuck along a scratch or a crack in the surface of the chocolate chip, then it's very easy for them to get together because they can't miss. I mean, if I've got one CO2 molecule right here and another one is wandering back and forth on a line and can't move off the line, then eventually it's almost certain to bump into this one. And if there's something special about one spot, maybe a place where 2 scratches intersect, that holds the molecules to that spot, holds one molecule to that spot, and then when another one comes, holds another one there, then it makes it much easier to form bubbles. So it's the roughness of the surface of the chocolate chips that accelerates the formation of bubbles. Okay, so what's happening in this thing? The chocolate chips, once they soak up a little water, are heavy. They sink to the bottom. Then, by this process, bubbles form on the surface. And when enough bubbles have formed on the surface of the chip is buoyant, and the bubbles draw the chip up to the surface of the soda pop. At that point, the bubbles burst, liberating the CO2 into the atmosphere. The chip now sinks to the bottom again and starts over, makes more bubbles, rises to the top, liberates the bubbles, and then the chips sink. So the chocolate chips are speeding up the process whereby the CO2 goes from this being very ordered state of being inside a small volume to a disordered state of being anywhere in the room or anywhere in the atmosphere. And in exchange for speeding up that transition from order to disorder, the CO2 sort of returns the favor, so to speak, by doing work or providing energy to the chips by way of lifting them off the bottom, lifting them up against the pull of gravity. So the energy that's created here is lifting the chips up repeatedly off the bottom. And that comes from this transition from a very ordered system of the CO2 in the small volume to a very disordered situation where it's in the large volume. So I've been teaching physics for many years and been used a number of different demonstrations. I'm really in love with this. It so elegantly illustrates a very, very deep concept. This is the second law of thermodynamics at work. This ultimately is the principle by which an automobile engine works, but illustrated in a very different way. I think this is beautiful. Thank you very much. So are there any other questions? I'll be happy to answer them.
Thank you. That was well done.
Thank you.
Good demonstrations. Lots of principles. Thank you.
Here, let me get this out of the way. Thank you. Great. Thank you. I saw you come in with your kids. The triangle is the strongest, simplest shape. I mean, the square is much